So where we had left off was I'd asked each of you to take a look at this R code and to draw a model that demonstrates the R code. So basically all of you guys sent that to us. And here's the picture. I did upload these slides already to Blackboard, so the new class slides are up. The picture I have here, I actually drew it with SPSS's program, AMOS. And there are a few things I want to note. The first thing is that basically everybody got the one-way arrows correctly drawn. So you all were able to see clearly how regression equations translated into boxes and one-way arrows onto your drawing. The one thing that was a little bit harder for folks to remember was to draw error terms with every single endogenous variable. And remember, an endogenous variable is one whose variance is being at least somewhat explained by other variables in the model. And so as soon as as soon as a box has a one-way arrow pointed to it, then it is an endogenous variable. And every endogenous variable must have an error term. The other way that you know it's an endogenous variable is because it is the dv in one of these equations. And as you know, all of these equations actually include some error associated with them. So we want to make sure that we remember to draw those errors. Let's see the other thing. I'm just going to try to bring up the chat box. Okay. Then the next question had to do with the covariances. And I'm putting something in the chat box and also will respond here momentarily to Morgan's question. So default in R is to automatically draw two-way arrows between every endogenous variable and every other endogenous variable. So what a lot of you did was, a lot of you just didn't draw them, which is okay, but if the code had specifically said that the say correlation between GPA1 and SMA was, I'm sorry, it's the double tilde. That's not, didn't give myself enough space. GPA1 tilde SMA was 0, then this arrow would not exist. But since the R code didn't have any of those specifications, the default in R is to draw absolutely every one of the two-way arrows between every exogenous variable. And remember, variable is exogenous if it is never acting as it's never being predicted by other variables in the model. Any questions about that? Overall, you guys did a really, really nice job with the drawing, the moving backwards and forwards. And we're going to get more practice. A couple of you had also asked about how to make the drawings pretty, and we're not going to worry about that. If and when you're ready to do one of these for publication, then I can talk to you about some different programs to make them really, really pretty, or some R possibilities. But for now, we're just going to stick with scribbles on a paper or whatever the default R is. Okay, so we had talked a little bit about some theoretical limitations to path analysis before. One of the things we talked about was how you needed theory in order to specify the model. This is not an exploratory technique. This is a confirmatory technique. We also talked about how after you look at your model, and here I actually added in a little bit of information about what the R code looks like. After you specify your model, if there's anything with your model that could be improved, if you include this argument in summaries, then it's going to tell you how to fix your model so that it fits the data better. So going backwards, let's say that this model here is the one we had specified. And in the end, what they told us is, what R would spit back is, really discrimination doesn't predict anything. So if you delete these arrows, and also math is really important to predicting job score. So if you also add this arrow, then I would fit a lot better. And so, to the extent that modification indices take your original theoretically specified model, and then you start to suggesting fiddles with it, it starts to suggest things you should do, like deleting certain paths or adding certain paths in order to fit the data better. It is no longer confirmatory, it is now exploratory. And to the extent that you are now in exploratory territory, you really have to suggest or ideally even conduct a second study where you cross-validate the new model. So then the model was originally confirmatory, then it became exploratory based on what our output modification indices were. Now you need to confirm that new model in a new sample, which is what we call cross-validation. We already talked about causal modeling last time as well. I believe that we were talking about all of these things, about the practical issues that were associated with path analysis and why it was, a great technique, but basically anything that messes with the integrity of a correlation is going to be a problem for this. So if the sample size is small, you're going to get unstable estimates. If your data are missing in a systematic way, then that's problematic. If they're missing at random, then you want to use estimation techniques that don't reduce variance. You're also needing your variables to be normally distributed, both at the univariate and at the multivariate level. Although, as I mentioned, and we won't cover it in our class, but we would in SEM, there are estimation techniques you can use that allow you to estimate non-normal data. You don't want to have outliers at the univariate or multivariate level. You want to make sure that your data are linearly related because this is just a bunch of linear regressions. If they aren't linearly related, you can always model that nonlinearity by adding in a sort of a x squared, or if you need to, even the cubic version of x. As always, we're talking about doing some matrix division, so multicollinearity is problematic and singularity will cause your model not to converge. We have a question here about how problematic are unequal variable cell sizes. It sort of depends. In general, when you're trying to predict anything that's a low frequency event or a low base rate, anything, so if any of your variables are skewed or if any of your predictors, dichotomous variables are, most people fall in one category versus another, then you may have problems, mostly around the stability of the estimate of that path. So let's say that you have a sample where 95% of your sample is female and only 5% is male, and you wanted to use gender as a predictor. It's going to be really hard for gender to predict anything because male is such a low frequency category. So potentially that's where it shows up, is that it's an underpowered variable. Did that answer your question, Josh? Awesome. And of course, we want our residuals, which we will examine, our residuals to be normally distributed and centered around 0 and small in absolute size, just like when we looked at our residual correlation matrix after EFA and PCA. Okay, so in terms of the big computational picture, the path analysis and the whole family of SEM techniques really focuses on the drawings. We really like the idea of being able to articulate what are our models, our theoretical models, through the use of these pictures. And we use those drawings also for any diagnostic purposes. So if we ever have a situation, which we will have, where your model either doesn't converge or where you have bad model fit, the pictures and the estimates can help us figure that out. So one thing that happens when we get excited about drawing pictures is that pretty soon we're going to realize that you want to draw more complicated models than your data actually allow you to do. And part of that is because the degrees of freedom of a model in SEM and in all of its sub-techniques is not a function of sample size anymore. So even if you have, like in our case, we have nearly 3,000 kids, that is not the sample size, or that is not the degrees of freedom associated with our model. Instead, our model degrees of freedom are a function of how much information we put into our matrix, meaning sort of how many variables we have, so how many data points in some ways, and how many parameters we are estimating. How many things are we trying to learn from the input data? So degrees of freedom become a function of the variables in the model and not a function of the sample size. And I'm going to show you more details about that in just a bit. In general, the steps that you take when you conduct a path analysis are you start, as we talked about last time, by specifying a model. And in R, the specification is done by actually drawing those regression equations, writing out those regression equations. The next thing you want to do is make sure your model is identified. And identification is referring to the degrees of freedom in your model. You want to have positive degrees of freedom. So DF greater than 0. If you have DF equals 0, this is something that we call a just identified model. And if you are trying to estimate more information than you have degrees of freedom, then you are not going to have, the thing won't run. You just will not be able to get any model information. So knowing how degrees of freedom work becomes important for path analysis and SEM. And I'll have a little bit more to say about that in a moment. Then we actually run our model. So we estimate it. After that, we look at the summary, which is an evaluation of our model, and we see if the overall model fits. And finally, and a little bit more controversially, is the modification step, which is asking the question of whether there's anything that we could do to our model to improve it. But again, these 4 steps are all confirmatory. But as soon as you go to this step, now you're moving away from confirmatory and into exploratory. Also, modifications are a little bit like doing stepwise regression, or statistical regression. Which modifications is recommended by the program depends on the specific data points you have. And so if you have anything about your sample or your data that's a little bit unusual or artifactual, that can show up under modification and is yet another reason why we want to cross-validate. And this will all make more sense in lab as well, because we're going to follow every one of these steps. Okay, so model identification. We've spent a lot of time the last time talking about specification, so now we're going to move into the other steps of running a path analysis. I said to you that the model needs to have degrees of freedom that are greater than 0. If you have degrees of freedom that are equal to 0, that's what we call a just identified model. And the problem with a just identified model is it's a little bit like me saying, okay, I'm thinking of a number between 1 and 1. What's the number I'm thinking of? Like, there is only one solution. So you're always going to get a perfect answer. But that does not mean that it's a perfect model. It just means you gave me no wiggle room. As another maybe more pertinent COVID example, imagine that your preferred toilet paper is Charmin, but you go to the grocery store and the only thing available is AngelSoft, and there's like one role or one package left. No matter what your preference is, you're gonna go with the one thing because it's the only option you have, so you have no degrees of freedom to express any preference. So the model looks like it's a perfect fit, but it's actually may not be perfect, just like Charmin may not be perfect, or AngelSoft, or whatever the toilet papers you prefer. It's just that that's the only thing you allow the model to do. So we don't want just identified models, we want models with positive degrees of freedom, so we can figure out if they're actually good models or not. To calculate the degrees of freedom for a path analysis, of course, R will do this for you, but it's the number of unique pieces of information in a covariance matrix minus the number of parameters that you are estimating in your model. And so the precise formula for calculating degrees of freedom, for calculating the pieces of unique information, the covariance, is P times P plus 1 divided by 2, where P is equal to the number of variables in your model, measured variables. So in the example where, let's say we have GPA 1 and SMA predicting job score 3, how many pieces of information will be in that model? Josh says 3. That's the number of variables. But what is the number of pieces of information? Casey says 2, Jake says 5. Everybody's all over the place. How many variables are in that model? Yes, 3 variables, GPA 1, SMA, and job score 3. So if we put that 3 into this formula, we have 3 times 4 divided by 2, which is equal to 6. Okay, so we have 6 unique pieces of information in this model. Now let me show you how number of parameters estimated works. Okay. Every arrow counts as a parameter. So right now we have 2 arrows. So that's already, remember that in this case we had 6 total, right? So that's already eaten up 2 of them. Plus, what else do we have in this model? We have a covariance between our exogenous variables. So that's a 3rd one. Plus, we have an error term or residual associated with estimating job score. So that's a 4th one. Plus, we have the variance, typically variance in GPA 1 and variance in SMA. And so suddenly we have eaten up absolutely every one of our degrees of freedom by just having this very simple model that really looks like it's only drawing 2 paths. So it is really easy to eat up degrees of freedom in path analysis, which is why many of the path analyses that you'll see published include low degrees of freedom. Some of the papers I've published have paths that only include, say, 2 degrees of freedom. So we're going to learn more. That your book also includes a little bit more information about how to estimate parameters, but let me just tell you, it is super easy to end up with a model that is not identified. So Josh asked if that's the main reason for needing a large sample, and the answer to that is no. The main reason for needing a large sample is because you're doing simultaneous regressions, and regression already is a pretty large N method, especially if you're trying to estimate things where you anticipate the paths or the effect sizes are going to be somewhat small. So the larger sample size N is associated with more stable estimates. The way you build degrees of freedom in SEM is actually by using latent variables. And I'll show you when we talk about CFA, how a latent variable buys you a ton of degrees of freedom. So, when you're doing path analysis, you run a real risk of under-identified models or just identified models. But as soon as you move away from path analysis with only the measured variables as predictors and criterion variables in your model, then when you add the latent factors, you buy yourself a ton of degrees of freedom. Latent factors don't exist in your data set, but they're indicated by multiple variables that are in your data set. So imagine that if instead of discrim, one, which is a variable in our data set, we instead were estimating discrim with a latent factor that included those 5, discrim 1, discrim 2, discrim 3, 4 and 5. Now, instead of it being one piece of information, it's one variable, but it has 5 pieces of information that go into it. So it's one of the reasons that we like SEM more than path analysis, but we'll get there eventually. Okay. So you want to make sure your model has positive degrees of freedom. After you've done that, you run your model through your program, model estimation in R. The model estimation, there's lots of different methods for estimating a model, just like there were a lot of different methods for doing an EFA and a PCA. So some examples of things you might see published include maximum likelihood or unweighted least squares or generalized least squares or elliptical distribution or Yuan-Bentler. Yuan-Bentler is great for non-normal data. So, but for now and for our purposes in our class, we're just going to focus on maximum likelihood. Jake asked the difference between a latent variable and creating an average score. It's a great question, which I'm going to answer in the lecture for CFA instead of now. But keep that in mind. I don't want to start confusing the latents with the path analysis and all that. Let's just focus right now on the one. All of these multiple methods for estimating your model differ in terms of how they handle small sample sizes or non-normal data, or if they do bootstrapping or all these different things. And again, your textbook and other resources would be a good place to look. We are just going to focus, like I said, on maximum likelihood because we have spent a lot of time trying to make sure that our variables are normally distributed and univariately normal and multivariately normal and all that other stuff. So we can just go right into maximum likelihood. I do have an article up on Blackboard, and it's an important article in terms of writing up your models if you're ever going to do a path analysis or a CFA or SEM, that it's important, just like with EFA and PCA, that whatever statistical decisions you make, such as using maximum likelihood to estimate your path analysis, that you justify your method of choice. So not just report that we used a Yuan-Bentler test statistic, but given non-normality in our data, we used a Yuan-Bentler test statistic, something like that. That way you're explaining to your reader that you're not just following defaults and kind of doing it in a sort of blindly dumbass way, but that you've really thought about, here's what I'm doing and here's why I'm doing it. Maximum likelihood and generalized least squares are good options when you have medium to large samples and you've met assumptions of normality. Smaller samples are handled with Yuan-Bentler well. Unweighted least squares we basically never use because it doesn't give us the overall model fit statistic. So it's an unusual one to see. It's kind of more old school. Again, maximum likelihood is probably what you're going to see most often. But if somebody says they're using it, make sure they've met all the other assumptions associated with these techniques. Okay, so after we've done our model estimation, then we want to run our summary. And now we have to figure out, okay, so how did the model do? Overall model fit is kind of our macro evaluation. As you know, in all of our techniques, we start off by looking at big picture, overall, how are we doing? And then it's only after we look at the overall picture that we are then moving into more micro assessment. So overall model evaluation is that macro level assessment. So the first thing is that everything flips on its head as soon as we move into path analysis and SEM. We want our model to be not significant. We are dying for a p-value greater than 0.05 if you have set your stated alpha at 0.05. And the reason for that is because as a confirmatory technique, we are drawing a picture of what we think should happen. Okay. And in the end, we want the computer to tell us that the data, the sample data, are not significantly different or not inconsistent with the model that you drew. So this model that I drew with variables 1, 2, 3, and 4, for instance, assumes that there is no direct significant path between 1 and 4, that instead there is a mediated path between 1 and 4 through 3. And I would hope that my data are consistent with the model that I drew. So my chi-square test is fundamentally answering the question of whether the data are significantly inconsistent with the model. And we want the answer to that to be no. We definitely don't think the data are inconsistent with the model. So we're looking for a non-significant chi-square. This trips people up quite a bit. Once you've got it, you've got it. But the first few times, people get excited when they see a significant chi-square, and you should not be excited. So now you're also going to see, especially as we move into latent variable modeling with SEM, that chi-square is often significant, even when you have otherwise a good model. And it's partly because it is a function of n, and these are large n designs. And it's also partly a function of model complexity. So the more complex your model, the more likely it is that there's going to be a place where it doesn't fit well. But it might not be a very important non-fit. It might just be like, well, it's a slight deviation, but it's really not an important deviation. So everybody and their mother has invented a different way to evaluate the model besides looking at the chi-square. And in your textbook, Tabashnik and Fidel talk about some of these. So one example, and again, all of these are more suggestions. The TNF book also provides the original citations for where these suggestions come from. But if you're doing a paper where you're writing a path analysis, you do want to tell your reader ahead of time, this is how we're going to determine whether our model fit the data well. So a good fitting model will be indicated by a non-significant chi-square, a chi-square to degrees of freedom ratio that is less than 2 or less than 3. It depends on which one you pick. Tabashnik and Fidel talk about people suggesting either one of those. A chi-key information criterion, or AIC, values. So if you're ever comparing two models, for example, if we're comparing a model that has variables 1, 2, 3, and 4, we could compare a model, right, with direct paths, and we could compare that model to one that eliminates the direct paths. And so if we run the model 2 times, I told you some of the best things you can do is to compare 2 models against each other. Both of these models will end up with an AIC value, a chi-key information criterion value, and whichever one has the smallest AIC is considered to be the better fitting model. The other things that you're going to look for are in fit indices, and there are tons of these. I believe in our homework, we're going to see a very extensive output. You don't have to, you can specify smaller amounts of output, but it's helpful for you to see just how many things you could possibly be looking at. But these are some of the most common ones. The comparative fit index is the CFI. And then you have a Tucker-Lewis index. You have a normed fit index. All of these, and there's a ton more. There's just a ton of them. Goodness of fit index is another one, GFI. There's just a ton of them. But basically, all of the fit indices are evaluated depending on who you cite at values above 0.90 or 0.95. So if your model has a CFI that is above either 0.90 or 0.95, depending on who you're citing, then that's considered adequate fit. The other thing that we might look for is the standardized root mean residual, or SMR or SRMR. And this is basically a standardized error. And so of course we want our errors to be zero, close to zero, and normally distributed. And so you're hoping that the standardized root mean error, so basically your average error, is close to zero. And in most cases, we decide that that means it's less than absolute value of 0.08. And another residual index is the root mean square error of approximation, which we are also hoping for values of less than 0.08. Some people say 0.05. Again, it's really important that you specify in your analytic approach what you're going to decide a priori indicates a good model fit, because there's lots of different ones. Now, I told you there's a lot of controversies in SEM and path analysis. This is one of them. There are some purists out there who say the only model evaluation that you should care about is chi-square. Everything else is justification for bad science. So if you have a chi-square that is significant, that tells you that the model and the data are significantly different from each other, and you should stop all presses, just discontinue and say, this model sucks. And you shouldn't try to make it not suck by, it's a turd model, and you can't make a model pretty by adding a flower on top of a turd. So basically, they're the purists, I consider them, who say any significant chi-square value is an indication of poor model fit, and everything you do after that should be focused on the fact that the model is not good. Now, not a lot of people fall in that purist category, and some that do are they're pretty interesting characters. Most people fall more in this, like, well, this is important, but it has problems. It has sort of a high false alarm rate. And so it is really important that we look at other indices. And there are times when you might learn something important, even if you recognize that you're not fully replicating reality. In fact, by definition, the model must be a condensed version of reality. And so I fall in the area of it's important to look at things from multiple perspectives, but recognize that A, not everybody believes that, and that B, even if your model passes with flying colors, all of these does not mean that it's actually a right model. There are times when a model can look consistent with the data through all of these estimations, and yet it's still wrong. Maybe it's wrong because temporally things are different. Maybe it's wrong because a really important mediator is absent because it wasn't even measured. There's no way for the model to know that it's missing. Maybe there's an important theoretical or conceptual variable or path missing. So even though your model may look beautiful by all of these standards, that actually doesn't mean that it is right or true with a capital T. It only means that it is not inconsistent with the data. That's a conceptual issue. We are not going to be able to look at that statistically. But please recognize that you might be missing something important, even if your model looks good. And that's actually true for every model. Questions about overall macro fit? Good question, Josh. Why would you use more than one or two fit indices? Are they different in important ways? So they are all slightly different in terms of their calculations. For example, the Tucker-Lewis is accounting for basically parsimony. So unlike the CFI, which is calculated by, well, it's functionally 1 minus a variable called T for your specified model divided by T for the null model. And T in this case is a non-centrality parameter, a non-centrality chi-square. Notice that nowhere in that calculation do the model degrees of freedom come in. They're absent. Whereas in the Tucker-Lewis, they basically take the chi-square for the null model minus degrees of freedom for the null model divided by degrees of freedom for your specified model times the chi-square for your specified model divided by, take that whole thing, chi-square for the null model minus degrees of freedom for the null model. You don't really need to know all these calculations, but you can see from comparing these two equations that Tucker-Lewis includes how parsimonious is your model. It's recognizing that models with a high number of degrees of freedom, meaning there's more ways the model could not fit, are basically riskier models. And therefore you shouldn't be punished by having a model where you have much more opportunity for the model to say, I don't fit well. Normed fit index is basically like the Tucker-Lewis, but it doesn't include degrees of freedom. So there are lots of different ones. You typically will only see one or two reported. CFI and GFI are the most common, but sometimes you'll see Tucker-Lewis if you want to do what's called a parsimony adjusted model fit. These things are different from these things, and in particular different from this one. This is the only indication, SRMR, or standardized root mean residual, the only indication about what happened to the residuals or the error, how much error is your model making. So the other ones don't focus on error, they focus on fit, and this one focuses on mistakes. So it's usually the case that we report a chi-square, at least one of the model indices, and at least one of the residual fit indices, one of these two. That's the most common thing you're going to see. Most of the time, people do not report everything because it's just overwhelming. But the other thing is that these things are all tend to be pretty associated with each other. So if you have a good CFI, then there's a really good chance you have a good TLI and NFI and GFI. And if you have a small SRMR, there's chances are really good that you're going to have a small RMSEA as well. So it tends to be a little bit redundant, kind of like the differences between PC and EFA. Any other questions about macro fit? We're going to practice all this, and we're, again, as we look at our lab output, it'll help us. We're going to come back to the slide and remind ourselves of, like, what does this tell us about our model? Okay, so after we do macro fit, assuming for a moment that what we found was an indication that the model overall provided good fit, then we can go on to a micro evaluation, which is where we actually start to interpret the path coefficients. And that's really where we get into the, like, okay, but what predicted what and how much and what didn't predict what and so forth. So each relation within the model can be evaluated for statistical significance. Every path, both a one-way arrow and a two-way arrow, will have an associated significance test. And these we want, again, to be significant at our conventional levels. So overall, we don't want significance, but at the individual path level, we do. And the most common way that we estimate the path and do a significance test on them is by using a z-score. So you take the B weight or the unstandardized estimate, and you divide it by its standard error, and then you get a z-score. And any z-score that is greater than 0.196 is significant at the 0.05 level. Any z-score that is greater than 2.59 is significant at the 0.01 level, and at any z-score of 3.33 or greater is significant at the 0.001 level. And this is for two-way tests. Now, our output's just going to tell us all that for us. We're not going to actually have to look at the z parameter estimates and then remind ourselves of their values. So we're gonna get information from the output about the specific standardized paths and their significance. Oftentimes, you're going to present your results not in a table, but in a picture, because again, it's easier for your reader to understand information that's conveyed in a picture. And a lot of times the path diagrams that are presented in manuscripts will include standardized path coefficients or parameter estimates in the diagram so that you can see it a little bit easier and you can compare things easier. If you don't present standardized coefficients, but instead you present the unstandardized, then you can't actually look at the B weights directly and tell which one is, quote, more important or stronger than the other. And that's why a lot of times the paths in path model will be standardized. So if I see my variable 1 and my variable 2 predicting variable 3, and my beta is 0.15 here, and my beta is 0.30 here, which variable is more strongly predicting 3? Exactly. My second one is. But if I hadn't put these as betas, if I'd put them as Bs, they could be something like 1.09 and 0.33. And you wouldn't be able to tell. I mean, you'd look at that and you'd say, oh, it must be 1, but it could actually be 2. It just depends on the original unit of the variable 1 and variable 2. So that's why we like to present standardized, so that somebody can just look at the picture and get a lot of good information. So in a moment, I'm going to show you that the same article, the Anton article that I opened with, and I'll show you what they actually found about burnout and job performance. Okay. The very final thing is our model modification. And again, this is another controversial area of path analysis and SEM. Model modification is done to improve fit if you're going exploratory, or potentially to test hypotheses in theoretical work. For example, there might be a theory of attention that says that attention relates to performance, but it only relates to performance in the context of, I don't know, low stress or something like that. And so you're wanting to basically look at the moderation effects. And another theory might say, no, attention relates to performance, even in the context of high stress. So it's assuming that this path doesn't exist. And so you could modify your model by including that path or by deleting that path. When you do 2 or more model comparisons, then you're going to conduct what we call a chi-square difference test. So our first model, let's say that it had 2 degrees of freedom and it ended up with a chi-square value of 5. And let's say that our second model, where we no longer drew that path from the moderator, so we gained a degree of freedom, and that had a chi-square of, let's say, 6. Okay. Our chi-square difference test is the subtraction of the of the full model from the nested model. So imagine these in reverse. So it's a chi-square difference. You take 2 and subtract it from 3. That leaves you 1 degree of freedom. You take 5 and you subtract it from 6. So that gives you 1. And this is what we call our chi-square difference test, which we can then look at a chi-square table, chi-square with 1 degree of freedom, and see if this exceeds the critical value. And again, this can be done on the computer, but the important thing is that it allows us to see whether a model with more or fewer degrees of freedom fits significantly worse than the other model. There are 2 other types of model modification family of indices that we look at. There's the Lagrange multiplier test and the Wald test. The Lagrange multiplier test will tell you, if you have a model, it will tell you basically, let's say that this is the model, okay? It will tell you, I would fit a lot better if you just put a path between me and this other variable. So it's going to tell you what you should add to your model to improve fit. Okay. In contrast, the Wald test is going to tell you what to delete. So if this was your original specified model based on theory, the Wald test would basically said, you know what, this variable here really is not related to this variable here. So I would actually fit just fine, not worse, if you just deleted me from the path. So getting rid of that arrow is what the Wald test will tell you to do. It tells you how to make a model simpler or more parsimonious without degrading model fit. And we're going to do these in lab. Okay, questions? So Josh asks if sometimes it makes sense to do exploratory model checking, and the answer to that is absolutely yes. Again, you might get some really hardcore people who say no, that at that point you're just fiddling, but I think a lot of it depends on what you do with your exploratory techniques. So in my mind, if you specify a model and your model doesn't fit well, and there is evidence that there are things you could do that would make it fit better, instead of saying I'm confirming a model, I would instead say, okay, well, now this is me being more in my observation role and my exploration role. So if I were to add this, then it fits better. So now to me, it generates a hypothesis. Like, is it always the case that the, say, attention affects performance through I don't know, say focus, for example? I guess that's kind of the same thing, but you get the picture. So I think if you have a poor fitting model, that you really owe it to yourself and your participants who spent a lot of time giving you data to really go in and explore why it didn't fit well and how it could fit better. But you have to recognize you cannot present that now as, aha, I knew all along, and basically commit what we call a hark. Actually, I was just talking to Austin about this, a harking error, which is another version of sort of p-hacking. So this is when you hypothesize after results are known, or hark. So if your original model had been, I think that these two variables relate to this fourth variable mediated through this third variable, but then your data suggests that actually this variable too isn't just mediated, it's also directly related. If you then take this and turn it into a publication where you hypothesize full mediation for variable 1, but partial mediation for variable 2, and then you present your results and say, I found support for both of my hypotheses. Variable 1 or 3 fully mediated the relation between 1 and 4, but it only partially mediated the relation between 2 and 4, then you have just lied. And lying is never good. And so what I think is the most ethical way to do it is to be clear, either through pre-registration or just as you write your manuscript, this is the model that I think is going to happen. And then you run the model and you say that model didn't fit well. And here's the ways it didn't fit. And you report your fit indices and whatever. And then you said examination of Lagrange multiplier test suggested the addition of a path between 2 and 4 would significantly improve model. So you put that in your post hoc analysis section of your paper. And then in the discussion, you talk about it as the hypothesized model did not fit the data well. The post hoc analyses suggested there might still be a direct path between 2 and 4. Now we got to go replicate it in a new sample. Okay. So I think it's very important for you to be super ethically clear and honest about what came first, what is pre-hoc and what is post-hoc. Okay, so another question came in. What if the model did fit the data well originally? Would it still be worthwhile to go through modifications? The answer, again, is sort of like, it depends. I think if your model fit the data well, but it was sort of marginal, and then you looked at Lagrange and Lagrange said, it's fine, but I really would fit better this way, you could still write up a post hoc analysis section of your paper. Just be clear that it's post hoc. I mean, just don't lie about the fact that you went from confirmatory to exploratory. If it really didn't make much of a difference, then I probably would just not do it. We are going to do this in lab. So we're going to specify a model. We're going to see that it's just identified. We're going to see how we can maybe delete some parameters using our wild criterion. We can also look at potentially how we can improve model fit using Lagrange. And then we'll have to talk about how you would write that out. Any other questions? Okay, so this is what happened with the Anton study. If you remember, they had originally hypothesized that to the extent that someone experienced role conflict, they would experience more role ambiguity. And in fact, they found support for that particular hypothesized path. By the way, I should say the overall model was not significant in a good way. And the parameter estimate, standardized estimate, was 0.26. They further hypothesized that if you experience role conflict and role ambiguity, that would directly negatively impact your job satisfaction. And they found support for both of those hypothesized relations. Then they further suggested that if you had high job satisfaction, you would be more committed to your organization, sort of emotionally committed. But that if you had more role conflict, or more role ambiguity, you would be less affectively committed. So they found support for the relation between job satisfaction and affective commitment, but these hypothesized paths from role ambiguity and role conflict to affective commitment were not significant. They further hypothesized that having affective commitment would be related to lower turnover intentions, higher job performance, and lower absenteeism, and they found support for all of those hypothesized relations. They found that role conflict was related to turnover intentions. The more conflict you experience, the more likely you were to want to leave your job. But they did not find, as they thought they would, that role conflict would impact job performance. They did find a relation between job satisfaction and turnover intentions. So if you were unsatisfied, you were more likely to want to leave your job. They found that the more role ambiguity, the worse your job performance was, but that role ambiguity actually did not predict turnover intention as they had originally thought that it would. And this is their final model when they trimmed. So this one, remember, this had a lot of like not significance, not significance. So they trimmed those all off using the Wald test. They took away those non-significant ones, gained some degrees of freedom. And this was their final model for predicting turnover intentions, job performance, and absenteeism. And that concludes our path analysis lecture. So any questions before we transition to R?